So, now the other, chapter 15 is the other kind of function. It's not, there's something similar. It's not exactly the same. And the treatment is also can be similar. But usually you compare that to the radial part. So this is the equation coming from the using the spherical coordinate, and the theta equation will give you this one, right? Right, so that coming from the separation of variable solution, and the theta part. Which equation should we? I mean, so first is this 15.2. If you go back to the PDE chapter, the separable solution, you see something like that. This is the theta part of the separable solution, and minus m squared square theta. This m is coming from the azimuthal part of the solution, just like the usual e to the im phi, so m squared multiplied by theta. L times L plus theta. Zero. And this L times L plus 1 factor, we consider that using the series solution, and show that you require that this number to, so that the function, the solution will be regular at the end at theta equals 0 or pi. So, or if we later on do a change of variable x is just defined as cosine theta. X equals theta is 0, x is 1, theta is pi is minus 1. The theta is from 0 to pi, x is from minus 1 to 1. And so at x equals minus 1 to 1, for regular solution, you require the series solution to truncate, and after it truncate, it requires condition to truncate, and so you get the the constant becomes L times L plus 1, and L is from 0 to infinity. So there are different possibility. Okay, and all right. So this is in the original variable theta. If you do this transformation, then the function phi become p, and this equation will change to I think we need some of the, I mean, without actually working on this transformation, where we just copy this equation, which is very straightforward. You can do that right away. So p double prime is ddx, right? And p is a function of x minus 2x prime x and minus m. Sine square theta becomes 1 minus x squared. This cos theta equals to p, or p equals theta, doesn't matter. Okay, and then you convert this to this equation. Now there's two cases. The first case is m equals 0. Just basically forget about this term, and And then the rest is called the Legendre equation. And we say that it's two cases because for the characteristic of the solution is there's a significant difference or the fundamental difference between the two cases. For COM, this P, the solutions are polynomial. So it's power of X, basically. And we see that there's some property related to the polynomial. And then for finite M, because of this factor, this is a factor that is that will come in to the solution. The solution is not purely a polynomial. It's a polynomial multiplied by some fractional power of 1 minus x squared. So that is those are called a Legendre function. So that is so we'll discuss that a little bit. So it's more complicated, obviously, is of finite M. Then so we treat it after we look at the property of P first, and then use some of the property of this the Legendre polynomial to get to the property of Legendre function. It's okay. So there are two cases. So first you consider M equals to 0 first. So, and then the solution, we usually just, for given P, the solution is P sub L, right? And then obviously this is second order equation, so there should be another solution. So there should be two solutions. But we consider this vector solution, which are vector at the axis plus or minus 1 at the two ends. But there's a possibility that sometimes if you're not considered the whole range of beta or the whole range of x, then you might need the second solution for the Legendre equation. And I think most people call it P, call it Q. So you have P and then Q. That one, if you're including the whole range, that function will be singular. It's not just like when we evaluate the series solution. So we see that the endpoint can be singular. So you can define a singular solution with this another solution with singular behavior near the endpoint. Just like you have the Bessel function, and which is vector as x equals 0, then you have Neumann function that is singular near x equals 0. Usually, you include x equals 0, you don't need Neumann function. Likewise, for the theta part, if you include the axis, which is theta is equal either 0 or pi, then you don't need the other function, the other solution. You don't need the singular solution. You only need the P sub L. Okay, and we usually call it P sub L, but then later on, your text will call it P sub N, which is fine, just whatever you want to call it. Right. The rest of the time, just keep defining this P sub L or P sub N in your textbook. The one way to define this is through the generating function. This, like what we did for Bessel function. This generating function for the Legendre polynomial, for this case m equals 0, is given by this one. 1 over square root minus 2x plus t squared. And equals the sum over this d sub n e to the power of n. Right. And I mean, at this stage, it's not obvious why these coefficients satisfy this differential equation with m is 0. but we could show it. I mean, there's more than one way to show it. So one way to do it is just following the Bessel equation discussion. If you remember that Bessel equation is, we start with a generating function for this j or this j sub n integer power Bessel function, and so we define j sub n at first, and then we derive the recurrence formula for j, right? And then the two recurrence formula, we derive that using the generating function by taking derivative of the generating function, and then from the recurrence formula, we show that whatever that those functions satisfy the recurrence formula also satisfy the Bessel equation. So one way to show that these are following this the same method to define this using this generating function, define this p sub n function, and then we can derive the recurrence formula for this p sub n using this generating function by again taking derivative. And now using the recurrence formula, we can show that these all these objects, say by p sub n, we can satisfy this Legendre equation. Now, obviously, this becomes n times n plus 1. Okay, so that is one way to do it. That probably can have other way to do it. And so, all right. And another way to write down, the other way to show it is using this to calculate so this is an expansion in t to in power of t, right? You get the p sub n. So p sub n is function x, but by the expansion of this the generating function in both t and x, then we get the power series expansion of this p sub n. Okay, and once we get that power series expansion, then we compare with what we got from the ODE chapter, the power series solution for the Legendre equation, which we did before, and using this condition to truncate the series, right? And that compare with that expansion, and then convince ourselves they are the same, and then so that this is actually what we defined before. Obviously, the series solution doesn't fix the constant, but in this generating function, the constant, this p sub n are fixed because you have already chosen this, right? One way to see that is for special values of x, like for x equals 0. All this p sub n is 0. But this becomes the coefficient becomes constant, and the generating function becomes not 0, I should say, x equals 1. 0 is difficult, x equals 1. Right, 1 is much easier. Becomes x is 1, so 1 minus 2t plus t squared. And that is, and these are considering that t is less or equals to 1. And when in this case, when t equals 1 is singular at 1, but we assume we can still do that. That this becomes 1 minus t squared, and then square root becomes 1 minus t, right? And that expansion is trivial, right? You all know how to expand this. Right? This is 1 plus t squared, all that, right? And so compare this with that. You can see that right away all the p's of n at 1 is 1. All right, so that is straightforward. So this means that you define this Legendre polynomial using using the generating function, then automatically fix the normalization for all these this function by the boundary value or at x equal 1, or the Legendre polynomial equals to 1, right? And later on, we'll show right away that all these piece of n's are even for even n and odd for odd n, right? So that automatically you see the p n minus 1 is equals to minus 1, right? Because n is piece of n is even function for even n. So for even n, then obviously that minus 1 is the same as 1, so it's equals to 1. For odd n, it's odd function becomes minus 1. So that is also straightforward. And that you can actually also use it using this expansion because x is minus 1, this become plus, and this becomes a alternate series, right? 1 minus plus, and then you can see that another way to do it, right? And then the next one is slightly more difficult. I mean that I'm going through this equation. Next one is it's like what I tried to do at first, the x equals 0, right? That is so x equals 0. And g is equals to, this is 0 becomes square root of 1 minus 1 plus t squared, right? And automatically you see that it's the power of t squared. So some of the you make it a power series of t to n. So all the odd terms, if n is odd, the coefficient must be odd, must be 0, right? Because this is only a power series of t squared. You only see that the Pn 0 is 0 for odd n. Then that's another way to see that this piece of n's are odd function for odd n. So obviously at 0 it must be 0. That's the trivial result, right? But then we can also do an expansion explicitly, and this expansion is a binomial expansion. It's a binomial expansion of the t squared for t squared. So it's minus one half power. 1 plus t squared and minus 1/2 power. You're using the notation in your textbook is this bracket function 1/2 of n to n. This is from I think this is from the 1.74 in chapter 1. If you forget about all these, look at that 1.74. That is there's the different form. I think the final form cited in your textbook is the last equation. So this is that this object is, I mean, compare with the right hand side is n0 into the, I mean, because of the fact that odd are 0, so we consider just even. Right? A piece of 2n0 is this object given by this object. And by this equation 1.74 is this minus 1n. And this double factorial n Okay, so are you familiar with binomial expressions? So you know how it come from. Right? I mean, sometimes you are writing is this double factorial function, especially for fractional power. Sometimes it's you write it and using gamma function also. This is this whatever you call it, combination coefficient, or you said binomial coefficient. What else you call it? Yeah, I mean, for integer power is trivial. So if it's integer power instead of fractional power, so that m and n is symbol defined as m factorial. For integer n, m and n, n factorial, n minus n factorial. Right, and for fractional m, then one way to write it is using gamma function. But the gamma function also can convert to this for this half integer thing. If you do it, just consider property of the gamma function. You can do it all. I mean, you can go back to the definition 1.68 to show that for fractional power you get this result. So it's straightforward. So this is the final property we look at today, and then we can try to look at other things on Wednesday. Is it okay up to here? Okay, let's then continue this Legendre polynomial. Again, there's also some tedious struggle with Legendre polynomials. I think we got the 0, and now the next property is 15.12. It's also an important property that is basically saying the Legendre polynomial of order n, the highest power of x is x to the power n, right? So whatever p sub n, the highest x power is x to the power n, and then work out the coefficient for that one. So basically, you start with the generating function that g equals to minus 2xp plus p squared equals to sum over m p sub n. That's a function of x and t to the power n. Right. Then now the next step is for this particular one, you are doing a binomial expansion for the whole this to both as a single term. And the next one is when you try to get the power series expansion for p sub n, you actually separate it in two steps. But for this consideration, we just do a binomial expansion. You're treating it this one as one single variable, right? So that is just using binomial expansion. This is a minus 1/2 factor. So it's using this symbol minus 1/2, and this whole thing is t squared to the n power. Okay, and for this consideration, you only want the higher order in power x, right? Because this the highest order is It's obviously you find the t sub n. The f p sub n is proportional. It's the coefficient of the term t to the power n, right? So, and the highest order of x would be the coefficient in front of this one, because when you take the n power of this one, this is t to the n power, and then there's a coefficient proportional to x to the n power. And you can convince yourself that there's no more terms in the coefficient of t to the power n that has a higher power in x, because all other terms will involve like a combination of this term minus times this term. But any times you multiply by this term to combine to a t to the power n. I mean, this two n they don't have to be the same, because ultimately you want the power of t to the n to compare with this. So you can, if you would like, you can just use another symbol as n pi, or using this as n pi, right? But to get to the t to the n, you still need the n power of this one, because every t power will carry an x power. So it's the n power of this one give you the highest power of x in the coefficient, right? So that's the argument, right? So whatever the coefficient of this term to the n power, it's the coefficient of p sub n, right? So you can say symbolically, you can say p sub n x equals to the coefficient of this one, which is now y1/2 n, and the power of this one to the n power, right? And then multiply by t to the n power. I mean, t to the n power is calculating out. So the leading order is that. So first, you can say order x n minus 2, because they are always increase or decrease by power square. So they are either odd and even. We're already sure that they're even odd. So for odd n is an odd function, for even n is an even function. So the x power is always decreased by 2. So you say that the leading order x to the power n has this coefficient, and the rest has a polynomial with the highest order is x to the n minus 2 power. So, right, so that actually is useful. It's useful property. So to always remember the highest power of p sub n is just x to the power n. Okay, and now the rest is to work out the coefficient. This coefficient is, given in the textbook, but let's see if we can structure with that. So it's minus 1/2 of n and minus 2 to the n power. Okay. Let's consider this one. This one is, there's a binomial, the coefficient of the binomial expansion. You can go back to chapter 1 to say that, but there's a general formula. It's like if you have m n, right? If m n are both integer, positive integer, then that's trivial. You will all remember that. N factorial, n factorial, n minus n factorial, right? You all remember that. But if m is not m is the power of whatever the power is of the binomial function. I mean, that's the function you want to do the binomial expansion. So if this power is not an integer, say whatever that is, like p or n, right? Then you can generalize this to like m factorial is just gamma m plus 1, right? So So you generalize that to gamma p plus 1. N for n is always an integer. Now this is p minus n plus 1. But that is we can use the gamma function to express this kind of object. Right? I always found this maybe easier to memorize this, because this one is you can easily memorize, and then you can convert this to gamma function, you get the correct formula. And okay, so and then so I mean, this is not the most compact one, because it has some redundancy, but it's allowed you to memorize the formula a little bit better. I mean, at least for me. So now we just substitute this 2 into here. So this is gamma p now is minus 1/2. So this is just gamma to the 1/2. I mean, gamma of evaluate 1/2. Okay. And then divided by n factorial. Now it's gamma. So minus 1/2. That's 1/2 minus 1/2 minus n. Okay, so I mean this is you can say this is a final form, but there's simplification if you like to convert, to cancel, at least cancel this factor and get something that not involving gamma function anymore. So then you just use the basic property of gamma functions. Gamma z plus 1 is z gamma z, right? That's one. So what you want is to get rid of all this n, right? So you do that. So every time you can, I mean, increase by 1, right? Increase this by 1 by divided by the argument, right? Every time you divide it by the argument, gamma z is gamma z plus 1 divided by z, right? And then you just keep going, right? Keep going, and then finally, so you increase. If you do it n times, do it 1 time, you increase by 1. Do it n times, you get rid of this minus n. Right? You know what I'm trying to do is just use this formula to keep increasing this, and then finally get the gamma to the gamma evaluate 1/2 and cancel this 2. Right? So that is the goal, and see now what we got. So every time you want to decrease, I mean, divided by the argument, so basically multiply by the argument. So multiply by the argument, you have 1/2 minus n, right? Or you can say, use the common denominator 1 minus 2n, right? And then the next one is multiplied by, the next one becomes already plus 1, but you only keep increasing it, so it's this plus 1, right? So it's another 2, and this plus 1 is common denominator becomes 3 minus 10, right? And then 5 minus 2n, 14. Altogether, you do it n times, right? That's what our starting point. You do it n times, you get rid of this minus n. You do it n times. With 1 time is 2n minus 1. Do it 2 times is 3. N time is, what is that? This is this is 2n 2n minus 1. 2n minus 1, you get n is 1, and then you get 1. 2n, n is 2, you get 3. Yeah, 2n minus 1. So the final terms is 2n minus 1 minus 2n divided by 2. Okay, so altogether you have n bracket, right? And so now you can reverse the sign of each one of them. So this is minus 2 to the n factorial. Altogether you have n bracket. So you have altogether you want to reverse the sign. So taking the inverse of the numerator, so the minus 1 to the n of them, and change that to just the numerator. So so you change it to n minus 1 because n is larger than 1. So 2n minus 3, 2n minus 5, altogether is that become 1. And then you have altogether 2 to the power n. Okay, now you see that all these cancel, minus 1 cancel, 2n cancel. So this is, and there's a notation for this kind of objects. That's a double factorial. Okay, see if I got it correct. So that's equation 15.13. Okay, that's how we get this. So if you don't want to memorize this equation, or you don't look it up, then every time you need to structure it, right? But it's not too much of a struggle. It's just need to be a little careful, and then you get the final answer. So that's this object, and so again, this go back to here. The coefficient is basically this one, and then basically this one. This one is because this is already including minus 2n. So this is 15.13. Yeah, that's included this one. So for just this just coefficient of the binomial expansion, you need to divide it by this minus 2 to the n to this one. So you only multiply this. But anyway, that is how you get that. So that turns out to be important too, because we sometimes want to know the leading order of this Legendre polynomial. All right, so that's this one, and the next one is a lot of structure. I think this is an exercise. You want to struggle yourself, try to see if we can get 15.14. Is that okay? So try this first. If you don't get it, then we can go through it in class. So basically, just write it out explicitly. I mean, it's not too much of a struggle actually. Just need to be a little careful in like change of variables kind of thing. Just need to be careful about shifting all these indices. So by this, basically now you're doing binomial expansion, but doing 2 times, right? You have because you have t in here, you have t in here, so you have each one has say like what we did before. So you have treating as a single variable, right? And then you have a binomial expansion. But this has 2 kinds of power of t. You have t linear and t square, and then to a certain power, like when you expand it, this power n. Then this one for each of these power, you still need to do a binomial expansions to get the power of t. So and then you collect all the power of t to form a form like that, t to the power n. and whatever the coefficient will be now a series, and actually it's a polynomial in X, and that you identify as P sub n, and that the final form is like that in X. Except it's writing in some kind of reverse order of X. That's fine. And this notation is they take n divided by 2 and the integer that is less or equals to that. So it's summing over k to something less or equals to n over 2, right? You know what I'm saying? N over 2 is equals to equals or small, large, I should say, largest integer. Smaller equals to, because n can be odd and even. If n is even, that's equal. If n is odd, then you divide it by 2, then you just take the integer that is the integer part, so you left the 1/2 term, right? And so basically, it's separate into 2 cases, whether n is odd and n is even. But anyway, that's the notation. Minus 1 k. Say that again. Great. Yeah, you can say this the greater integer, but I don't know whether this is a common notation. I'm not sure. Just the square bracket, but the textbook defined like that. But anyways, this need to be a little careful of the notation, and the rest is factorial to n to k factorial e to the power n k factorial minus k factorial minus 2k factorial, and then x to the power n plus minus 2k. Okay, so it's kind of an inverse power, so because you always subtract the k. I mean, you can, if you like, you can go back to say define this as another index and sum over this index in the increasing order of x. That, but this is now written in a decreasing order. That's fine. And then you can combine that, compare that with the series solution we got from the whatever we got. I think it's actually in chapter 8, but we at that discussion we didn't actually write down the form. We only considered the ratio of the coefficient between two terms, and that depends on whether n is odd and even. Then we got a form of that, and actually the argument was you need to truncate that, so somewhere along the line that ratio becomes 0, so the rest of the series becomes 0, and that is important because if you don't do that, then the series solution diverge at x equals to plus or minus 1. So that's the discussion, but supposedly you can use this form and compare with that solution and convince yourself that this kind of expansion satisfies the same ratio of that discussion. All right, but that also a lot of work to do. But anyway, that's at first you work on this exercise first and see if you get it. All right, and once you have that, you can do a different thing. I mean, you can also use this kind of thing to derive the recurrence formula. That's one possibility. You can also show that going backwards, this is generating function. You can use this form. This is your explicit form, and then show that substitute this form into the Legendre equation. See that satisfy the Legendre equation. That is also possible. I think that is also an exercise, if I remember correctly. Yeah, I forgot which one, especially that could be another exercise. But anyway, there's multiple way to show that this is the correct. I mean, the generating function is giving you the correct form of the Legendre polynomial.